what we are going to do now is start with the baseline rotor and see if we can optimize this using automatic optimization in Turbo Design 1 in order to achieve the stage total pressure ratio target. And as the degree of reaction is high for this stage, it should be sufficient to optimize the rotor while keeping the stator the same. So here is the workflow used by the optimization, where the blade loading and stacking parameters are used to generate the blade shape in TD1, and then the resulting performance parameters are fed into the optimizer, which basically applies MOGA to drive the solution towards the optimum design. And of course, we need to start by specifying the range of variation for the input parameters, which are the stream-wise loading parameters, and also the work coefficient at the shroud, because it has an influence on the tip leakage loss. And whereas by default the ranges are plus minus 10% of the baseline values for each parameter, as you can see here, but there is a machine learning based feature in TD1 that can provide initial range estimates for these stream-wise loading parameters. And this is because we want to explore a large design space but also try and avoid infeasible solutions. And then these are the constraints that were used. So we constrain the throat very tightly to plus minus 1% in order to maintain the choke margin. And then the diffusion ratio is also limited to avoid the possibility of flow separation. And finally, for the optimization objectives, we want to minimize the profile and the leakage losses in order to hit the desired pressure ratio levels. So once the optimization run is complete, which is very fast and takes about 15-20 minutes or so on a single core machine, we can see all the designs on a scatter plot between the two objectives, the profile loss on the x-axis and the leakage loss on the y-axis like this. And the target case, which is the baseline rotor, actually sits here. Now we can also choose to see only the feasible solutions which respect all of our specified constraints. And then we can choose to see the Pareto front of optimum designs, from which we can select any design of interest for a further analysis. And in this case, we select a design from around the middle of the Pareto front, which promises a good trade-off between the profile and the leakage losses. And so we use this design for further analysis and for comparison with the baseline rotor. And in fact, this is what has changed as a result of the optimization. So for the span-wise work distribution, you can see that compared to the baseline rotor, the optimizer has tried to reduce the work at the shroud in order to suppress the tip leakage. But since the mid-span work was kept as fixed, the hub work is automatically increased in order to maintain the same overall work as the baseline rotor. And then for the stream-wise loading, you can see that compared to the baseline rotor, the optimizer has tried to make both the hub and shroud four-loaded in order to reduce the profile loss. And as a result of these changes, the optimized rotor is looking clearly very different from the baseline, as you can see here. And also, if we look at the Mach number distribution in TD1, then it actually looks much smoother compared to the baseline at all the different spans from the hub to shroud. And also the peak value still stays well below 1 for this subsonic compressor. And here are the results for the optimized rotor, and it's interesting to see the effect on the Turbo Design 1 parameters, where we can see a significant reduction in the profile and the leakage loss parameters as a result of the optimization, with only a slight change in the throat area and the diffusion ratio. And when we actually run stage CFD with the new rotor, what we find is a notable improvement in the stage total pressure ratio, such that it's now able to exceed the target value at the design point. And at the same time, the stage efficiency is also maintained well above the TD pre-prediction. And then finally, a quick look at the streamlines on the rotor surface, and here we can see a more well-behaved flow, especially near the suction surface trailing edge in case of this optimized rotor.